should have used these analogs. They're excellent climbing analogs for all this off-policy RL. Like imagine learning to climb without actually trying by seeing small snippets of video people making some move, another move, another move. And then like you're supposed to be an expert at the end because you have seen many of these videos.
You mean a new route or just like climbing in general?
Huh?
You mean a new route or climbing in general?
Climbing in general, like you never climbed.
Right.
Because that's what our agents are like. They have no idea about physics or anything, right? Like in general. And so we expect them from these little snippets to paste everything together, come up with a plan, and do it.
Mm-hmm.
Wow, very, very ambitious. Very ambitious. It's like you're climbing a lot before you start to feel that, like, you know, some of the moves, right?
Yeah.
And then still, then there is so much to be learned, but none of that is learned without experiencing it. You all learn it by experiencing it.
But
Sometimes, okay, people tell you things. Drop knee, do this, do that, right?
But I guess this is a little bit different, right? Because you're making a distinction there between like experiencing it and like watching it is different. But here we don't make that distinction. You know, like if you get a snippet and you see the reward, that's the same as if you were an agent in the real world and saw the reward. Like there's no distinction between these two things. So like the difficulty with batch, right, is like claiming that we don't have the snippets, like the videos.
Yeah, the videos are not giving trust to your joints. It's not your body. It's a different body. Yeah, that really makes it even more difficult. But
so that's like but like if it is your body, then like, you know, when you're watching videos, you'd still make the claim that like, you know, watching the video of you executing the policy is different than like you doing it yourself. But for the agents, it's not different. In a sense, like if you have if the policy that you want to evaluate and you have that data, that's sufficient. It's the same as if it ran it on like using, I don't know, online and had that
the
data.
same data.
Yeah.
Sure. Yeah, it's okay. So it's a broken analog. It's every analog. Everything is broken, but okay, it was a good try, right? Okay. Back to batch RL. So what was going on? The last time it was all about coverage. In feature space. Which was the conjecture that if this minimum eigenvalue condition holds, that somehow the design matrix underlying the features and the data that you see, there's an expectation, and then that, and this is poly in 1 over H, 1 over E. Then this is going to be sufficient to get, what were the acronyms of policy evaluation, getting off the ground, of policy, the optimal value estimation, or even optimizing in an off-policy way. And we have seen that by and large this doesn't work. That was the last time. So there is no algorithm which can get away just with a coverage condition like this. So then we can start blaming the coverage condition. And in a way, that's what we were doing, right? Like we said that, maybe in a tabular case, you would not have the data. If you have the data this way in this counter examples, and of course you don't see the reward, you cannot learn. So it's like this condition is coming from supervised learning, Supervised learning, yes, this is necessary and sufficient for learning a target function, and this minimum eigenvalue, the inverse of it, is going to show up in both the bias and the variance of least squares, and actually any estimator. So you can prove lower bounds that say that like any estimator needs to use samples which are proportional to the inverse of the minimum eigenvalue if they want to control the variance, and the bias blows up at least with the inverse of the minimum eigenvalue. So that's supervised learning. And so in reinforcement learning, the difference to supervised learning, so supervised learning is basically this problem, roughly, with h equals 1. And so in reinforcement learning, we expect h to be large, and our interest was, okay, like in h equals 1, things work out fine. You have polynomial sample complexity in RL when h is large. You have seen this result, which was by and large, it's like something like d over 2 to the power of h. So if d is sufficiently large, like 4 or something, or 3, it's the smallest number for which the base is greater than 1, that this is exponential growth with the horizon, so things are getting exponentially worse as the horizon is getting large. So that's lower bound. So, okay, but maybe this is not the right condition. In supervised learning, okay, we could defend it, but so maybe here, what we should be looking at is a better design, like some other condition. So why don't we allow more freedom, or we should be asking the question like, what would be, if this is not a sufficient condition for polynomial sample complexity, then what would be a sufficient condition? Is there a sufficient condition? Is it possible to come up with some design, some data collection design, which is completely passive, such that you throw this data collection design at the problem, you collect the data, after that you can compute with polynomial sample complexity all of these things. That is the question, right? So the process was always that you're designing a way of collecting data, then you collect data, then you use the data to solve your problem. And so here we were just saying, okay, in supervised learning, some designs do work, and then you collect the data, you can use the data to solve your problem, it's all fine. Does it generalize to reinforcement learning without any modification? No. No, we can go back. We can ask, like, is there a better design? Some other way of collecting data that would make everything work? Maybe there is, right? Like, since we couldn't solve it just with the supervised learning condition, we really need to take a step back and then ask the bigger question. All right, so in regards of this, unfortunately, this batch RL is just like the story of what never works. So, okay, so the results are going to be negative, and they're going to say that there is no such design. Okay.
But don't we know, like for OPP, where you're just trying to evaluate a policy, we know the design where we run the passive policy exactly as the policy we're trying to evaluate will be fine.
Yeah, but okay, so to make the question interesting, you don't know the target policy to be evaluated ahead of time.
Don't know it.
Yeah. But it's like, because if you knew it, then like, yeah, you would just like use that.
Yeah.
Yeah, that's a good point. So that's an easier problem. We know how to solve that. You can just do the rollouts, and you're fine. This condition gives you everything that you need.
Yeah. Okay, and then like Alireza mentioned last time, then start relaxing, like how close it is in terms of visitation
Yeah.
in places, because we're trying
So you
to,
can
that's the difficulty of like.
you can go
that's
that
the-
way, and then there will be some constants that appear that govern the sample complexity that depends on the divergence between the two policies measured in some way.
Yeah.
And then the question is how big the divergence could be.
Yeah.
In a way, all these are answering that question.
Right, but that's not quite like what you were saying where it's all negative, it's just like, at some point it becomes negative after.
Well, yeah, I mean, okay, so if you're asking a question that either is too ambitious and you get a negative answer, or it was not that ambitious and then you get a positive answer, all that is happening here is that the questions that initially do not look that ambitious turn out to be very ambitious. And I guess like it's important to know that these are overly ambitious, and then you have to scale back, and then I guess you can go from the outside, like from the most ambitious questions to the least ambitious questions, and that's how we do it.
Mm-hmm.
Most of the time, even for planning, we consider it's Q-star approximation only. Like, does it work? No. Okay, then like we have to do something more.
Yeah.
Yeah. So it's good. Yeah. Yeah. So maybe I shouldn't say it's all just negative results, because like at one end of the spectrum, obviously there are some positive results when you are basically in the own policy case, and then minor deviations from the own policy, you can still get pretty much the same results, but it seems that it's really hard to move the needle, so to say, further away, and it's very easy to run into these overly ambitious questions, which would have been nice to have a positive answer to. Just happens that they don't have a positive answer. The hunt goes on. Like this doesn't mean that like, okay, we asked all these questions. You can come up with some other constraint on the setting, and then that other constraint may just like flip things around. Like, for example, okay, let's say it's just LQR. If you're in like, you have other constraints on the system, I just made this up, so I don't know the answer, but like, just to illustrate, like you can make up arbitrary other things that might be relevant or irrelevant to your problem, but sometimes they're gonna be relevant, and then they're constraining the problem in such a way that suddenly something that was impossible in general becomes possible because of other reasons.
Right, but still, when you like draw that big picture of all MDPs and then you start, slicing parts and saying those are impossible.
Yeah.
Like really, all you're doing is just like finding some small chunk there for certain assumptions that things become possible with this, like who you're saying.
Yeah, so you could also say that you're punching holes into that space.
Yeah.
And then whether the holes are big or small is not a well-defined question at all, right? Like, there is no natural measure on like how big this space or this volume in the space of MDPs. There is no such thing. If there was a natural measure on the MDPs, we would just all be Bayesian and just use that, right? So it's like, yeah, we are punching holes.
Yeah, it's a good point that there is no natural measure.
Yeah, I think that's the struggle.
Mm-hmm.
That's why we are punching these holes, and then that's also, so in a way the negative results are punching these holes, and the positive results are encircling problems where things are fine. Like they point out other sets where things are fine. Whether something is big or not, I don't know. If you're lucky, you need to solve a problem, then like it happens to be on the good part. But it's like a huge blackness with a bunch of red dots here and there, and a bunch of green like floating stuff somewhere else, and that's it. That's what we know about these problems, right?
Yeah.
So every theorem that is here is basically just talking about this space, some part of the space. and coloring it red or green.
It'd be nice to have like a nice visual picture of that space and which ones are
I
negative.
think it's like it has so many aspects to it that
Yeah.
it's like it becomes challenging.
And it's hard to see the overlaps between the different
Yeah.
assumptions and
Yeah, it's like sometimes these sets are overlapping.
yeah.
These questions are actually pretty good, and like it's worthwhile to think about them, right? Like when people have started to make up assumptions like linear MDP, this MDP, that MDP, they're not independent of each other.
Is there any work
Really?
that tries to like, the whole purpose of it is to just draw out this giant map of which ones are within which ones and like the,
So yeah, sometimes people do draw these things, but
yeah, I've seen like small, like in their space of what they're working in, it's like
Yeah.
these are the common ones and these ones kind of imply other ones and stuff.
usually
it's
you have
like
your
that.
favorite and then
Yeah,
like how it relates to everything else.
yeah. It'd be nice to see like one unified picture.
Oh, you can do it.
Yeah.
Okay. All right. So how does this work? So there is this is a work by Andrea Zanetti. I think last year or something like that. And I'm going to talk about two theorems. One is for off-policy evaluation. And the way this is going to work is that this theorem is going to say that for every dimension and gamma, so in contrast to this, it will be the other way around. So it's like, it's more like h to the power of d or something. That's going to be the lower bound. So if d is large, then we're gonna get into trouble. But if d was constant, then we would be fine with larger and larger horizons. All right, so for every d and gamma, you can find a state space and an action space. And okay, these are not complicated. These are going to be just the d-dimensional unit ball, 2 ball, e2d, both of them. So it's nice and compact, but it's infinite. The infinite action space. And it has this linear structure, and that is going to be used pretty strongly. So there exists SNA. So why do we need first SNA without MDPs? Because we want a design that works for what? Like for all the MDPs that share the same state action space. Okay, so we fix a state action space like this, the unit ball, and then we allow any design. So we're gonna say that for all designs, and this is going to be so-called pi design or generalized pi design, G-pi design, because I was using pi design before. Pi design was just that when you are rolling out with some policy that you picked. So this generalized pi design is going to do the same, except that you could have multiple policies, finite number of them. So if you want to collect a sample of size n, then you would have a bunch of policies that are lined up, and it's completely passive, this data collection. You would have some initial states, so you have a state space, so you can like name some initial states. Like I want to run policy 1 from this state. Then you would say that I want to run policy 1 from this state for this many steps. Then you say I want to run policy 2 from this other state for this many steps. And so this is this generalized pi design. It doesn't have to be a single policy. It can be multiple policies. The starting state is fixed, and you have to say ahead of time how many steps you're going to take with each of the policies. Now we're going to allow like something that's going to look weird. We're going to allow to collect information about any state action pair that the policy can ever reach with positive probability, that is in the support in so many steps. The reason we can do this is because in the counter example, we'll have deterministic dynamics, so this says nothing. This doesn't allow the designer to do much, right? Because normally if you have a support and it's like you have a stochastic thing, then it spreads everywhere. And maybe it gets to so many states, but like if you choose deterministic dynamics, then this is very meager. Like it's not worth doing it, right? Like if you have deterministic dynamics, this doesn't give you any further power than to say that I just choose this state, this state, this state, this state, especially if I tell you the dynamics ahead of time. And this is going to be the case here. So in the counter example, we're going to have a fixed dynamics and only the reward is going to change. So because of this, we can have this super generality and it doesn't happen. And at all the states and the corresponding actions that the policy takes, I can give you the full transition kernel and the full reward, like without noise, like the immediate reward. There is no noise. And the construction still works, so you can feel that this is going to be a needle in a haystack in a way. Yes.
Wait, sorry, with one query you get the reward for all actions in a state?
No, not all actions, just the action that is chosen by the policy.
And that's different than if you had deterministic rewards or transitions? Isn't that exactly what you would get anyways? If the policy did that?
No, so here in the counter example,
Yeah.
we'll happen to choose deterministic transitions.
Mm-hmm.
So that takes away the power of like following policies because you can, and the dynamics is known because you can pre-compute where the policy is going to go.
Yeah,
So
yeah.
it's like, regarding the reward, we're going to have no noise in the reward, so we will have the deterministic reward function as well. And if you have that, this doesn't give you power either, right? So it's like, yeah, so we are not playing with noise. So that I think that's,
Okay.
like, since we are not playing with noise, we can allow this level of generality. Like some of the constructions, like for example, last time we were playing with noise. So the construction was predominantly, it was working because you had noisy information and you had to fight the noise. If you didn't have noise, that construction wouldn't have worked. In fact, you can ask the question, okay, if you guarantee that coverage and there is no noise in the MVP, so everything is deterministic, maybe then you can get a polynomial bound. I'm not sure about that.
And this is also
It's a stretch goal.
This is also like strictly more general than the Z design and the pi design we had
Yeah.
before.
Exactly.
Yeah.
It is generalizing both of them. But the extra part that it gives is vacuous, will be vacuous for the counterexample, but we are choosing the counterexample so that it has vacuous power, so we can say, even this more powerful design, you can try to use it, it's not going to help you. It just speaks for that, yeah, the dynamics can be known ahead of time, it can be deterministic, and the reward can also be deterministic. All right, so any row generalized pi design. So now it's clear what is that. And any algorithm that is sound. Okay, so there is some epsilon. So it's like we're talking about this policy evaluation problem where you're given a task of evaluating some policy, and the policy could be chosen adversarially, so this is what you don't know ahead of time. And you need to evaluate that policy at some initial state. And the epsilon and the data, so you have to evaluate the policy up to an epsilon additive accuracy. You just choose something, it's like, it doesn't matter, some constant, because it's a lower bound. So, yeah.
So, yeah, it is interesting the way way that problem is framed now, right? Where it's like, you're assuming that you want to get a good enough set of samples such that for any possible policy in the future, you can then evaluate it, right?
Yeah.
It's kind of like the view, which, yeah, then it becomes reasonable, right? Because if you have the view that, you know, you have some knowledge of like the type of policies you might want to evaluate, then you
would use
then
that.
you can start biasing how you would start sampling.
Exactly.
But here it's like, you know, you can, anyone in the future might, you want to be like able to support any policy in the future that anyone tells you to evaluate.
So you can, so related problem could be, and I think some people looked at this, but I'm blanking on what the results are, but you can speculate what they could be, is that you're given a finite list of policies, so you need to get some state in action space, and then you have a list of policies, and then you can ask the optimal design question. Can we design something that supports all of these policies? When can we do it? And like, I don't know how much research was in this direction, but maybe this is an interesting question because you can imagine that this happens. Like it seems practical that someone had like not a single policy that would be like outrageous, right? Like if you have a single policy, you just run a policy and you'll be, you can still ask whether you could do better by not running the policy, but doing something else, probably not. You can get an answer to that, but if you solve this general problem, then you would have a solution to that problem as well. This could be interesting to look at. Anyways, okay, so back here. So we have no knowledge of these policies, so it's all of them are possible, and here there are many of them. Of course, there is going to be, all right, so before that, you're given a feature map as well. And I think that in this example, the feature map will be something like, oh, just take the action. But that just happens to be the case. So any algorithm that is epsilon delta sound with or epsilon 0.1 and delta 0.1, there exists some policy. So the worst case sample complexity of, you know, getting epsilon delta precise estimates of the values of all the policies. So there exists an S naught in the state space as well. From S naught requires this many samples. So there exists a target policy such that this algorithm on this, there exists an MVP as well. So here, the transition probability and the reward needs to be chosen, and this is just going to be deterministic dynamics. So the next state, S prime, is equals to FSA, and it will just happen to be A. So you choose an action and you go there. And the reward is going to be a reward function over the state action space, and it will be between -1 and 1. Yes? You in? Question?
Oh, sorry.
Oh, mute? It's like when I talk to my dogs. Fire on a call. All right, okay. So it's like if this algorithm needs to get in this MDP the value of this target policy from this row optimal design, from this, sorry, not row optimal design, from this row G pi design, then the number of samples at which this can happen is at least h to the power of d. So this is what's happening. Okay, so how does this work? I'm not going to do the full proof. It's included in Andre's paper, and also last year I've already done it. And I should write it up.
I think there should be an assumption on the realizability of.
Oh yeah, like this doesn't make any sense. Like I forget. Yeah, cool. Yeah, absolutely. Like why do we have this phi here? So the target policy is such. Yeah, I forgot. Super crucial because like, oh, how would you do this? The target policy is such that it lies in the linear span of the features. Okay, so you're just looking for the coefficients and given the data. And okay, so how does this work? So the dynamics is going to be this linear dynamics, which is not sensitive to the state. So it's like, yeah, you can just jump anywhere. It's like the beautiful teleporting dynamics. That's gorgeous. And then the reward is going to depend on just the action, no, just the state, I think. And the way you should imagine it is that, well, this design, it's not more powerful than a Z design because everything is deterministic, right? Like following the policies for so many steps, it gives you a sequence of states. So you can just like list those states. You can pre-compute what they are. So you can imagine that all this design can do is that for every sample size, it lists what states it will look at. So it lists those states. And so these are the states. And then it can list the actions as well, because for each state, you can have a private policy associated with it. That's the most general way of doing it. So you have state action pairs, n of them, and they are somewhere. And you have this unit ball. And so now it's like we need to turn this into a needle in a haystack problem. So where do we put the needle? Well, whenever you have a sphere, then there are many needles on the surface. So when you have a ball, right? Like you have the ball, most of the volume is on the surface, so you just like put the needle in the surface. What is going to be the needle? Well, the needle is going to decide what is the value of the policy. So somehow the policy needs to be sensitive to like where the needle is. So long story short, what you can do is that you look at the sample, you find a hole where those on the left and the right, a small cap where you happen to go up to, I don't know, gamma with the radius. In this gap, in this volume, in this spherical cap, to no examples. If there are not many samples, the spherical caps have totally small volume. So if you don't have enough examples, then you will always be able to find this. That's just a volume argument. Such a direction that both of these spherical caps are empty. And then what you do is that you put in a reward function that along this main axis is going to look like this, and otherwise it's going to be linear. So we can go from -1 to +1, and we can stop at gamma or minus gamma. And so all the samples are here. So we don't want any reward there. So we put 0 reward there. And here, So this is also gamma. So this is 1 minus gamma. So we put a line that goes from negative of 1 minus gamma to 1 minus gamma. And in this little section here, we're going to let the reward to be either positive or negative. And so the target policy is going to be a policy that we can choose that. So we will choose the target policy in such a way that if it starts somewhere here, then it takes its times and eventually it goes here. And it goes here in so many steps so that the discounted total reward is from, I think the initial state is going to be just like 0. From that initial state, it's going to be either around +1 or -1. So it's not going to take too many time steps. So that's the target policy. And now you have to complete the picture. So the reward function is going to be chosen to be linear over the spherical cap and 0 outside of the spherical cap inside the ball. And the target policy is going to be a linear policy. And things are so that you can calculate that the value function is going to be linear in the future. So that's kind of like the nice part of it. Yes.
I guess in that picture you meant to erase the line in between the minus gamma to gamma.
Yeah. It's like this is dotted. Yeah. This is something like this. That's right. So this is actually the value. And now the argument is going to be the only way you can evaluate this policy is by having information in either this gap or that gap, and you don't have that if you don't have enough samples. If you don't have that information, I can just like flip from, to the negative of the reward, and the data will not tell you whether that was happening. Therefore, you're going to make an error at least on one of those words. Whatever value your algorithm is going to come up with, it's going to be a value. It's going to be at least far from either -1 or +1, which are the values of the policy at the initial state. Yes?
What that assumption was important, like being able to like model the Q function of the target. Oh, okay. Oh, it was target, not the log input.
Yeah. I mean, without that assumption, of course you can't do much.
This is about log
Things are
input.
very complicated, but yeah, we're still hoping that some of the features are going to happen. Yeah.
So I guess here that path from like the initial state can't take too long, otherwise that reward.
No, you can't. Yeah,
would be
because
quite
otherwise
small.
it diminishes, right? So it's
Yeah.
like it has to go quickly enough. So it's in a way the study of linear dynamics with linear policies, and how long does it take to get there, and it just, yeah, it's nice that it works out, but it does. Okay, so this is the first design. And So you can ask the same question basically for policy optimization, or estimating the value of the, to be precise, for estimating the value of the optimum policy. So this is for optimal value estimation. And the story, I think, repeats. I'm trying to think about like what is the difference? Is there a difference? No. The coefficients gets a limit first. So blah 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 Q star is in the feature space. So the concept, like the statement is really analogous to the previous statement. It's not worth repeating everything. And the conclusion is going to be that, I don't know, like in this case, it's like, okay, that all these constants as well. So here, like, okay, square root h is what's in the base, and here h is in the base. Actually, there is a factor of 2 there. But you get a square root b there, but like, okay, who cares? So here, there is a slight worsening of the exponent, which is like, yeah, do we expect that? Well, I didn't expect that, but I guess it's an imperfection of the construction. I'm pretty sure that this problem should be at least as hard as the other problem.
When you say worsening, it means like worsening in terms of the strength of the lower bound, or like
Yeah,
the difficulty.
it's like, yeah, this lower bound is a weaker lower bound.
Yeah.
I mean, like, it's only square root h dependence, whereas there is an h dependence, but it's like, is it that difference worthwhile of spending time on? I'm not sure. So one thing is that, you remember we talked about this Q star realizability, right? For planning. So what was the result that we were getting for planning for Q star realizability? For some similar problems. So here, the state space is the unit ball, the action space is the unit ball.
Also exponential.
It was exponential, right? So already for planning, and in planning, we have like active data collection, right? Like that's even stronger. So then what the heck? So for planning, under Q star realizability, no restriction on the number of actions. The lower bound was what exactly? Do you remember that? It was exponential in some way. We have two quantities, D and H. How do they appear?
D to the power h.
Huh?
I think d to the power h was
Not that one. That was that one, okay.
Wasn't in the number of actions? That's kind of what I remember. Maybe I
Well, that was the upper bound for tensor plan,
Okay.
which was kind of
It was e
foreshadowing this, but, huh?
e to the
Okay.
min of d and h.
Okay. So I will just write this 2 and then an omega.
Yeah.
Okay. So what this tells us is that if we have the luxury of being able to control how we're collecting data for a similar setting, then we get a big number if both D and H are large. So to get the set phase, we need, so for planning, which means active data collection. We need both D and H latch. So this is just like simplifying a little bit what we have learned. And so if we have this passive data collection, which is basically what we have here, then for the set phase, this is enough. Enough if these latch. And okay, so we had that result as well. So that's also passive data collection, but with good coverage. So it's restricted. It's like here the data collection is not arbitrary. So here we got a bad result or a set phase when H is large. This was more like a needle in a haystack, and this is more like needle plus noise or information theoretical hardness. It's kind of interesting. So here, stochasticity did play a significant role.
We don't know if it's necessary.
And we don't know whether that's necessary. I think that's the good question. We know, by the way, so here, stochasticity was necessary. For the sad phase, we had to have stochasticity. If we take away stochasticity, so where do I write that? N plus stochastic system. So it's like, but this is actually needed. It's like it's a rank column. It's not enough. That's actually necessary. If you have deterministic systems with active data collection, all is fine. That's Zheng Wan and Ben Monroy's old paper with optimistic constraint propagation, which is like tensor plan, just for deterministic systems. Yeah. So it remains to be seen whether what happens for deterministic systems in this case. This was fully deterministic, so we know that for deterministic systems with passive data collection, active data collection, all is fine, no matter what. Passive data collection, things are bad if the dimension is large, but we don't quite have the same result for the good coverage assumption.
Yeah, I was thinking the counterexample here are the stream state and action space with infinite. What if we have large finite state action space?
Wait, so in these results, they're not finite?
They are infinite, right?
Yeah, they're infinite, yeah, okay.
So what if we consider large MDP with finite?
Oh, like you can discretize this.
Discrete it.
Exponentially many, indeed, that will be enough. In a way, that's it, right?
Okay, construct
I guess it will be a little bit harder because you have to step from here and there, and like you have to have exact linearity, and you have to have some exact progressions, and like I don't know, like maybe it's a little bit, but my guess is it's gonna work. But okay, yeah, it's a good challenge. Let's put it that there. How about finite? Essay. Well, I don't quite know the answer for that conjecture that this concession just goes through. These appropriate modifications.
I think the second one goes through, but I haven't know how the first one.
Oh, you tried?
I haven't tried. I just think a little bit like.
Okay. I don't know. I would be surprised that if suddenly, like finite by arbitrary. Okay, so can we play games like? It's really hard to believe that finiteness would be a real restriction, right? Like countably infinite, sure, you can do it. Because rational numbers are closed and there are all these algebraic manipulations and like everything is nice and algebraic here, so you just take rationals and everything is countable then. But it's really hard to believe that something would break if you have finiteness, but okay, like you have the linearity assumption that's like constraining things, but I don't know. Yeah, so what other things can we think? Oh, another question that you can think about is your arbitrary designs, so these generalized pi designs, you restrict D to be small, you allow H to be large. This is the hard problem. We don't know. It's like, is the problem hard because here it shows that it's hard if the dimension is large, but like if we have a fixed dimension, it's not hard. I'm like, these are lower bounds, so maybe it is hard. Maybe some other example is going to show that, okay, planning long horizons is also hard. It would be surprising if, in a way, I feel that that should be true. Yeah, I would be really surprised if that was not true. So if you want to prove me wrong, you could try to prove an upper bound of this size. It can be exponentially large in D, that's fine. I don't think it's going to work. Huh?
I was going to say, I guess the lower bound would have to look quite different than this one. For that
Yeah, if you want to switch the rows or something like, or you want to get a lower bound like this.
I can't, so normally when we want long horizons, how did we put rewards that far away without them being useless after like a horizon of H? do we normally solve this problem in lower bounds?
Oh, like you are making the rewards exponentially smaller as you go towards the end. And at the end, like in all of these constructions, you get this tiny, like d to the minus h rewards with a mean of that, and like Bernoulli with that parameter, so you never actually see a reward. And somehow you can manage to boost them up back without the algorithm noticing. That's basically, that construction was also playing that game. And maybe for the deterministic case, right? So we were asking this question for the deterministic case. Maybe for the deterministic case, you can do something. I don't know. Because in all of these other constructions where we're talking about long horizon is hard, yeah, like something is stochastic. Like we have to notice. I don't know of any lower bound that would prove that long horizon is hard without using either stochasticity of rewards or transitions. That is it. And we have the upper bound for the active case, which shows that for completely deterministic systems, things are polynomial in D and H. Okay, so now you can draw another cube, I guess, with like deterministic, stochastic, and like D small, H small, oh sorry, D small, D large, H small, H large, and like, okay, in every little room, oh, passive active, and and then which of these cells are filled out? Some of them are filled out, not all of them are filled out, and whatever is left is pretty interesting, I think. To me, this deterministic stochastic is very curious. I think it's very curious. It's somewhat unexpected, if you ask me, because I expected some continuity. It's like there's not much stochasticity in these systems. I mean, okay, so there is bad noise. I think that there is enough stochasticity so when you execute the system at these lower bound constructions, you wouldn't see the stochasticity. Actually, you would see everything looking deterministic, and yet the system is stochastic, and that's the difficulty. You never see what, and then you don't know, right? So there's like things are really sensitive, I guess, like that. That's the.
So I guess to show that stochasticity is important, we just need an upper bound.
For what?
We just need an upper bound for these cases with long horizons.
Yeah, we never have any upper bounds for any of these cases.
Yeah.
If you try to publish a paper with an upper bound of this type,
Yeah.
good luck. I tried. Second submission succeeded. It's fine. Like you just have to say something about the curves and like big words and.
Or you just put the table and so you filled in this gap.
Should be enough. I think.
What was the problem? Like, I mean, what was the problem?
Oh, so
getting this accepted?
for which it was just the tabular case with by design, like that proof was never written down, and I said like, okay, why don't we write it down and send it? But it's going to be like an exponential lower bound in the horizon, and then a matching upper bound that shows you can actually do it with that amount of time. And they didn't like it. But it really does make sense to have a matching upper bound, because you have all these alternative proofs. So back to what you were saying, what people are doing is that you measure the deviation between distribution induced by the target policy and the logging policy. And then this deviation is an unbounded quantity. And your bounds depend on this unbounded quantity. So your sample size, even if you have a finite MVP, It seems that it could be arbitrarily large. But no, it cannot be arbitrarily large because you have a finite horizon planning problem. So eventually, you will get it. It just takes exponential time in the smaller of the number of states in the horizon.
Yeah. Well, I mean, none of these cases are closed, right, until we have them matching upper and lower bounds.
Yeah.
So
Yeah. It's
you kind of need both.
yeah. Okay, so back to this stochastic versus deterministic. Yeah, I think that it is. It is very curious because it is almost an arbitrary choice to make, to think that the world is stochastic. It's like, who are you to think that the world is stochastic? Maybe it is deterministic. If it's deterministic, everything is fine. Like, really, seriously? It's like, and then you switch to, that's such a small change. But, okay, the planning people, classical AI planning people, they kept saying that, oh, for stochastic systems, long horizons are really hard. Like, we don't ever want to do it, and so on and so forth, without any proofs. But there was a common sense that stochasticity just makes things really, really hard. So in a way, it's not unprecedented and not completely unexpected if you read that literature. But it's a choice that you make. Like, why do we make this choice? It's like, just think that your system is deterministic. Well, yeah. So what does that mean? In a way, it goes back to this. Like, you really have to think about, like, okay, so you're controlling this robot, and then can you ever get back to the same state? If you don't, then maybe it doesn't matter whether the system is deterministic or not. If you can, like, reliably somehow reset the robot, and then you try the same action and you see the different outcome for thermal noise or whatever reason, like, then it was really stochastic. But at a macro level, I don't know, that's philosophy, but quantum collapse, like, there shouldn't be no stochasticity. Stochasticity is like this convenient but somewhat lazy way of saying that, like, I don't want to model some details, so I just treat it as stochastic. But then it bites you. It says that, like, oh, stochastic, you want it stochastic? Yeah, okay, boom. Exponential lower bounds. But there is this, like, the whole field of machine learning is built on, looking at a world as if it was stochastic, even though we fully know it may not be stochastic or it may not matter, but, like, it seems powerful.
But we know when we, like, take a stochastic system and actually write out the underlying true deterministic system kind of view, the deterministic system should be much larger, right?
I don't know what you mean by this. Maybe,
like, let's say, like, some path can have, like, some probability of going down one pathway, and then some other probability, like 1 minus p of going some other trajectory, or some other state. Well, that's, like, if there's some true underlying deterministic reason for this, then to model that, we'd have to add in some new states in between, so that we know if we visited those, such that to deterministically know where we went then. So that kind of makes our MDP larger. So maybe that's somehow related to this. I don't know.
yeah,
When it's
it's true. Somehow, this related to this, but I wonder whether all of this is nullified when we say that our MDPs are big enough anyways, and we need to use approximations to solve them, so features and whatnot. So they already collapse. So even if you have a deterministic system, so many times what people are bringing up stochasticity because you could have this, like, view that, okay, you can measure up to this accuracy. So this is the accuracy. So, like, this is something that you need to measure, the space of that. So if there is something here, or there is something there, this is your accuracy, you're going to think that they are the same. There is an underlying deterministic dynamics. So from here, the system goes that way. From here, the system goes that way. So now it looks that it can go both ways because you were measuring with a finite precision.
Mm-hmm.
And so that's somehow related to this. And because of this, it seems that maybe it's valid to, or maybe it is helpful to think that the system is stochastic. At least we see that it could continue trajectories in different ways.
Yeah.
But when we are putting the features on the top of things, we're also doing this. We're collapsing these states, which are now, like many of these are collapsed together anyways. And if the underlying system was not treated stochastic, then we know that we won't run into any trouble with that. And we do run into trouble with that if we start to think that the system was stochastic. So I think that that's kind of like, you're doing the abstraction at the wrong point.
Yeah, because like in a way the stochasticity, like at least like the way we think of it, it's like it kind of like compresses the deterministic dynamics, or deterministic MDPs, and so do the features, right? They kind of compress the. But
They
then
have
so,
the
like why not just
same role. Yeah,
not
like
just
do it
forget-
once, like don't
Yeah.
do it twice.
Yeah, exactly. Why do it in two places, and why does the other one cause? Can we like combine them somehow? I don't know.
Yeah.
It's very odd.
So it seems to me that like, yeah, I spend a lot of time on the stochastic business, but
Mm-hmm.
it's not fully clear that we should continue doing it,
Mm-hmm.
especially in light of results like this that tell us that you can't do much about the stochastic case, yes?
So like I don't know how much it makes sense, but like if the features were kind of like from like they were compressing like they were expressing trajectories instead of states or something.
Mhm.
I don't even know how that would be
They do.
formulated, but
You can do that, yes, and?
then would that fix these kinds of problems that like if we're let's say we don't know if we're in this state or that state, that these states will lead to
So can you increase your resolution by using full history or something like that?
yes,
I
like
think you can to some degree, but it doesn't address its fundamental problems, like the gap between the complexity of planning in stochastic and deterministic systems.
okay. So I mean like instead of like compressing states that are in some way similar to each other
Mhm.
into one, maybe we can have the same resolution but compress the trajectories
Mhm.
that are in some way similar to each other into one.
Sure. I mean, like, I always think about the features of doing that. Like, there is no reason. So I write the features as a function of the states and the actions, but it's because we have the state. And if you have the state, you have the Markov property, you don't need the history. Like in any application, you won't measure the state, you measure observations, and then the features are going to depend on those observations, and they should depend on full history. That you can make a recursive filter, a very complex computation that results in features. That's how I'm thinking about the features, but by the definition of the state, they are still a function of the state because only the state is what matters. Right? It's just like equivalence classes or whatnot. And like, okay, so without loss of generality, I'm writing the features as a function of the state. But since the algorithms cannot access the state, this is not a limitation on how the features can be computed. The features could be computed based on trajectories, that's all fine. Yeah. So, troubling questions, eh? It's like all of machine learning collapsing. A lot of people believe that, like one revolution in machine learning was this probabilistic revolution when people brought statistics or probability theory together with machine learning. You had these graphical models and like you started to model data as random, things like that. And yeah, like is it going to derail everything when it comes to planning and doing other stuff like reinforcement learning. Maybe it does. Then like, why are we doing that? Okay, so then the real question is, okay, Sonnet is up to something because he's talking about completely deterministic problems and exponential complexity. So that's good. So that's the real bad example. Yeah. So what do you think? Should we just ditch stochastic problems? Get rid of probability theory. Life would be so simple. No measure theory.
Yeah. Yeah, I don't know. I was wondering, yeah, it still feels somehow like these stochastic systems, you can somehow, I don't know, feel just thinking like somehow you expand into an equivalent deterministic system that's much larger, that then has the same problem. But then you're kind of limited by, these assumptions that your H can't be too large, because then the reward is negligible or something, I don't know.
I mean, like the whole story wants to be that the number of states doesn't matter if you have good features, right? And that's, we are trying to answer this question.
Right.
And so if you're blowing up the state space and getting deterministic dynamics and rewards, but you can still have the good features, then all is fine.
Mm-hmm.
Except here we don't know.
Then it almost feels like the features needed to represent a stochastic system equally as well as a equal-sized deterministic system should be more demanding. Oh, sorry, maybe the other way around. Oh yeah, no, not the other way around. Like, it's like the stochastic system already has some loss from its compression of like the true underlying deterministic system, and then you ask for our features to still represent that as well as a deterministic system of equal size.
Okay.
So it seems like those features, it's harder to find those features, or they're more, like it's more demanding.
So then there is one more reason not to look at stochastic.
Yeah, I agree, but I'm just saying like, if this all is true, like that's kind of where the difficulty, because then since we make the assumption that these features are this good, we kind of skip across the fact that it's harder to have these type of features, or maybe that like these systems are harder to compress, like stochastic systems might be harder to compress with features than deterministic ones or something.
Yeah, we're never asking those questions.
Yeah. So in that sense, like it's now I see why there would be different. Like if we just assume the features are good enough, then yeah, sure. The original claim doesn't make much sense that I made, because we're just assuming we can compress it regardless.
Mm-hmm.
Yeah.
Yeah. All right. Did we have any questions in Slack?
Yes, we did.
Okay.
Why is the
No, I
first
think
one?
my question has been explained.
What?
My question has been explained. Like,
Okay. All right. Okay. If you don't feel like it.
And then Gabor.
yeah, I think my question might have been answered too, but the question was that, like in last lecture, we had this one Kakada result from 2020, and we had delta equal 0.1, and like also the epsilon was probably smaller. So I was just wondering if it makes sense to look at, or if the results are indifferent intuitively they should be, if we are less confident about the result and we have higher error in the policy, like would it make sense to look at that setting?
Right. So the dependence on epsilon and delta in the lower bounds. Yeah, it's like all these results are hiding these dependencies. There is obviously some dependence, and the authors are decided that it's not important to work on this dependence. I would only work on these dependencies if I have nothing, no better ideas, I think. or for some like, okay, so at the moment I don't see like why you really wanted to know this dependence. It's like usually it's log 1 over that divided by epsilon squared or something like that, which is hidden here. And like If the result would be something like that, then would that be interesting? Not really. If it was somewhat different, so if I knew the answer and it didn't look like that, but it looked different, then maybe yes. But the effect seems very small compared to these exponential constants that are multiplying these terms. So I think that that's in a nutshell why people, when they're proving lower bounds, they very often just do this, choose some epsilon, some data, and I don't care about epsilon and data dependence, because it's the usual thing. You expect to see the usual thing, but you have to work harder to get that. And yeah.
So even for very low confidence and higher, it's still exponential. It's just.
Yeah, I think that it would be. I'm not sure about this because everything is deterministic, but it's. So maybe here, since everything is deterministic, it's like, hang on a second, like what is stochastic here? There's nothing that's stochastic here. Nothing. So it's like, this was a fully deterministic result. I looked at, like where the horse, and I just put stuff there. So in this case, I don't think that letting data go to 0 would increase the lower bound. There is no noise. If you want noise to matter, then somehow you have to introduce stochasticity. Then you would have a log 1 over data to some power, probably 1, and over epsilon squared. And that's just Gaussian noise, right? Like Gaussian noise, like if you want to estimate the mean of a Gaussian, how many samples do we need for accuracy epsilon? Variance is 1. We need log 1 over that over epsilon squared. So it's like all comes back to that. And so if you allow stochasticity, then it all comes back to this Gaussian pair. That's what we use. And why Gaussian? It's okay. Central limit theorem, like you're seeing many random variables which are regular enough so that central limit theorem kicks in and kicks in pretty fast. It really looks like Gaussians. Data that you have. And so here you definitely could have the log 1 over data over epsilon squared. Here it's more like you can make epsilon smaller, it doesn't get worse. You can make data smaller, it doesn't get worse. And it's just this number. If you would allow stochasticity, I bet you can bring in a log 1 over data over epsilon squared. Somehow, mean of a Gaussian needs to be estimated to know something on the top of doing everything else. So that's how they combine. So here it says, you need to find a hole. And in the hole, you will have noisy data, okay? So now, in the hole, you have to work multiplicatively more to get the signs correct. Like, which way does the river go? Yeah. So that's a good point. Like, there should be no, okay, so generally this is how things are stated, but here it's like everything is deterministic. All right. That's it.